Welcome back to the deep dive. Today we're really cracking open the toolbox, you could say, for software development. Forget the specific languages for a moment, Python, Java, whatever. We're looking at the fundamental building blocks. You know, the structures, the rules, the conventions that programmers use everywhere to build code that actually works, that's accurate, efficient, and, well, reliable. Think of it as your essential programming kit.
Exactly. And our mission today is really to get under the hood, understand the mechanisms. It's not just about, memorizing commands. It's about really grasping how code deals with data, how it makes decisions,
Yeah.
and how it uses these standard recipes algorithms to solve tricky problems fast. We're digging for those core ideas that make or break performance and readability.
Right. So where do we start? I guess with the foundation itself, the data. That's C1 and C6 in our outline here. Every single program works with data. And yeah, we all know about numbers, but the real power, it seems, comes from how you structure things more complexly. Things like objects, records, and sets jump out immediately from the source material.
That's definitely a critical point. We sort of assume everyone gets integers versus decimals.
Hmm.
But the key is how you bundle related information. Take a record, for example. It lets you group different types together, logically, like maybe a student's name, which is text, their ID, an integer, and their GPA, a float, all in one neat package. And then you have sets, very useful collections where every single item has to be unique, no duplicates allowed. That's how you start building real structure.
Okay, so you've got these structures, but then managing where the data lives becomes important, right? Scope. That difference between local variables, kind of temporary tools just for one job, and global variables, the ones accessible from, well, everywhere. Why is there always that warning about overusing globals? What's the risk?
Well, global variables, they feel convenient at first, but they are inherently a bit dangerous. The risk is that any part of your program, any function, could potentially change that global variable, maybe accidentally. And that leads to behavior that's really hard to predict, hard to track down when things go wrong. Local variables, because they're contained just within their own function, are much safer, easier to debug, definitely. And managing that scope properly, along with using really clear naming conventions, that's absolutely fundamental for code you can actually maintain later.
Right. Clarity is key. Okay, so we move from these single variables, local or global, to more organized ways to store collections of data. The data structures themselves, C6. And it seems like there's always a trade-off, isn't there? Choosing between, say, lists, records, sets, and probably the most common one, the array.
The array is really foundational, mainly because it gives you that index storage, first item, second item, and so on. Perfect when sequence matters or when you need to loop through things easily. And the sources make it clear you need to be comfortable with both single-dimensional arrays, just a simple list, and multi-dimensional arrays. That's where you get the power to represent things like grids or tables, matrices,
Yeah.
much more complex data layouts.
So the insight here is really about picking the right tool for the job from the start. Like, if you need super fast lookups to see if something exists and you absolutely cannot have duplicates, maybe a set is the way to go. But if you need things in a specific order and you need to access them by their position, then the array is your friend.
Exactly. That choice array versus set, for instance, it's a fundamental architectural decision. It directly impacts how efficient your program will be later on when it's processing that data. We're talking the difference between seconds and potentially minutes of waiting time. Making that call correctly, that's where real developer skill comes into play.
Okay, so that's the structure, the architecture. Now let's talk about the engines, the things that actually do stuff with the data. The operations in C2 and those handy built-in functions in C3.
Right, Operation C2. We quickly go beyond just adding and subtracting. The sources highlight some specialized tools, particularly in division. There's a key difference between getting the standard result and getting just the remainder. That operation, often called percent or MOD, sometimes modulo, or even rem.
The MOD operator. Why is that one singled out? It seems pretty basic, just the leftover from division. What makes it so important?
Oh, it's incredibly useful. It's kind of the workhorse for anything involving cycles or checking even odd. Use MOD constantly for things like checking if a number is perfectly divisible by another or making sure an index wraps around correctly when you reach the end of a list. Even in areas like cryptography or generating hash values, it's where the math starts getting really tailored for specific computer science problems.
And those results, the true-false from comparisons or the numbers from math, they feed right into the program's decisions. That brings in the relational operators, equals, less than, greater than, and the Boolean operators, not D and D or IR. These seem to form the entire bedrock of how a program thinks, how it makes choices.
Absolutely. And building on that logic, we often rely on built-in functions covered in C3. These are like pre-built tools, already tested, ready to use, saves a ton of time. We see standard arithmetic ones like random or range.
Yeah, and speaking of specialized functions, the sources explicitly separate standard round from something called truncation. Why draw that line? What's the big deal, especially maybe in finance or science?
That's a subtle but critical distinction. Rounding, adjusts the number up or down based on the next digit. It can introduce tiny biases over many calculations. Truncation, on the other hand, is just chopping off the decimal part. Brute force. No rounding involved. This guarantees a predictable result with no rounding error introduced. So if you're dealing with currency, or maybe high-precision physics simulations, you absolutely need that control. You can't have approximations creeping in.
Makes sense. Control is everything there. And then for any program that actually talks to the outside world, string handling and conversion must be vital.
Oh, essential. Think about user input, right? Someone types 42 into a box on a web page. To the program, initially, that's just the character 4 followed by the character 2. It's text. You have to use functions to convert that string into an integer or a float before you can do any math with it. And then going the other way, you might use concatenation joining strings to combine text and numbers back into a message for the user. That conversion piece is the absolute bridge between what the user sees and what the program calculates.
Okay, so we know how to structure data, how to perform operations on it. Now, how do we control the flow? The actual decision-making path the program takes. That looks like control structures, C5, and also ensuring data quality, C4.
Right, control structures dictate the path. For doing things repeatedly, we have loops. The sources emphasize the main three. For loops, typically when you know exactly how many times you need to repeat something. While loops, which keep going as long as some condition stays true. And repeat loops, which are similar to while but always run at least once before checking the condition. And knowing when to use a break statement to get out of a loop early is also key for handling special cases cleanly.
And for the branching, the if this happens, do that, otherwise do something else kind of logic. The classic F, then else. But the sources also specifically call out elseif, or sometimes written as elif. Why is that structure so important for complex choices?
Elife. It's basically essential for avoiding what programmers sometimes call nested if-hell.
Hmm.
That's where you end up with if statements inside other if statements, inside more if statements. The indentation gets crazy and the logic becomes almost impossible to follow. Elife lets you check a series of mutually exclusive conditions one after another in a flat, much more readable structure. Hugely important for clarity.
And we also can't forget about packaging up reusable bits of code. Function calls, which involves defining the function, saying what arguments or parameters it needs to do its job, and then actually calling it when you need it.
Functions are really the heart of modular programming, making code reusable and organized. Now, if you connect this all together, using functions and clear control flow like ifs and loops, that makes sure your code runs logically. But all that beautiful logic can completely fall apart if the data you feed into it is bad. Junk in, junk out, right? And that brings us squarely to data validation, section C4.
Validation, the gatekeeper. It seems obvious, but why isn't it enough just to write logical code? Why the specific focus on actively checking the incoming data?
Because real-world data is messy. Users make typos, systems have glitches, data gets corrupted. A program is only as good as the data it works with. Validation is about improving accuracy and reliability, and the techniques mentioned are quite specific. Checking the data type is correct. Is this actually a number? Ensuring the data falls within an expected range like an age shouldn't be negative, a percentage should be between 0 and 100. Applying other constraints, maybe checking if a required field is actually filled in, using Boolean checks for true-false conditions.
And it's not just checking. The program has to do something based on the check, the post-check actions. If the data is wrong, you can't just let the program crash. It needs to, what? Tell the user, reject the input, ask again.
Precisely. Validation isn't just a one-off check. It's often part of a loop. Check the data. If bad, report error and prompt again. Repeat until good. It's about ensuring the integrity of the data before your main logic tries to process it. So yeah, control structures run the program's logic, and validation makes sure that logic runs on good data. In today's world, with data coming from everywhere, validation is like the essential firewall against errors and unpredictable crashes.
Okay, this is where, for me, it starts to get really interesting. We've got the data structured, we can operate on it, we can control the flow, we're checking quality. Now we need the actual recipes for solving common big problems efficiently. We need algorithms, C7.
Yes, algorithms are where the rubber meets the road in terms of performance, especially with large amounts of data. Two of the most fundamental tasks are sorting data and searching within data. For sorting algorithms, the sources point to three specific standards programmers should know: bubble sort, quick sort, and insertion sort.
Okay, three sorts, but just listing them isn't enough, right? For someone learning, what are the trade-offs? I always hear quick sort is the go-to.
Generally, yes. Quicksort is often preferred in practice because, on average, it's very fast for large, randomly ordered data sets. It uses a clever divide-and-conquer strategy. Bubble sort, on the other hand, it's
Mm.
simple to understand conceptually. You just keep swapping adjacent items if they're in the wrong order. But performance-wise, it's usually terrible for large data sets. Really slow. Insertion sort has its place too, particularly good for small lists or lists that are already mostly sorted. The key takeaway is that the choice of sorting algorithm can dramatically affect how long your program takes to run, especially as data grows.
And sorting leads right into searching algorithms.
Makes sense. It's easier to find things if they're organized. We have the basic approach: serial or linear search. Just check everything, one by one, versus the much faster-sounding binary search. That comparison really highlights a core principle in computing. Sometimes, spending time organizing your data up front, sorting it, saves you vastly more time later when you need to find something. Linear search is simple. It works on any list, sorted or not. But it can be painfully slow on large lists because in the worst case, you check every single item. Binary search requires the data to be sorted first, but then it's incredibly fast. It works by repeatedly having the section of the list it needs to search. Think about searching a dictionary. You don't start at A and read every word. You jump to the middle, see if your word is before or after, and jump again. That's binary search. On a list with, say, 1,000,000 items, the difference between linear and binary search is astronomical. It's the difference between getting an answer instantly versus waiting, possibly a long time.
Instant versus system freeze. Got it. And finally, implementing some of these algorithms or managing tasks in general often involves using specific structures like stacks and queues.
Right. Stacks and queues are fundamental data structures, often used behind the scenes in algorithms or operating systems. Stacks operate on a last-in, first-out principle, often abbreviated LIFO. Think of a stack of plates. The last plate you put on top is the first one you take off. Or think about the undo function in software. It undoes the very last thing you did. That's often implemented with a stack. Your computer's function call stack works this way too. The currently running function is on top.
Okay, last in, first out, and queues. That sounds like waiting in line.
Exactly like waiting in line. Queues are first in, first out, or FIFO. The first person who gets in line is the first person served. Queues are used everywhere. Order matters: managing print jobs, handling network requests, ensuring tasks are processed in the sequence they arrived. Understanding LIFO versus FIFO is really crucial for designing systems that manage tasks or data flow correctly.
Wow, okay. That brings us pretty much to the end of this deep dive. We've gone from the basics of declaring data, including complex types like records and sets, through using specialized operators like MOD and understanding truncation, controlling the program's flow with loops and conditionals, validating data, all the way to executing efficient standard algorithms like quick sort for ordering data and binary search for finding it fast. It's quite a journey.
It really covers the core concepts. So what's the big picture here? What does it all mean? Ultimately, mastering these programming paradigms, these standard ways of doing things, it's all about building structure, efficiency, and reliability into your code. By using these conventions for handling data, controlling execution, validating input, and applying the right algorithms, you ensure that the systems you build are not just accurate, but they actually perform well, especially as they scale up. Honestly, every single line of successful, maintainable code relies on a solid grasp of these fundamentals.
And maybe a final thought for you, the listener, to chew on as you continue exploring this stuff. We talked about those standard sorting algorithms: bubble sort, quick sort, and insertion sort. We mentioned quick sort is often preferred for general speed. But here's the twist. What if you have a data set that's already almost perfectly sorted with just a few items out of place? Which of those three methods, bubble, quick, or insertion, might suddenly become surprisingly efficient, maybe even beating quicksort in that specific scenario? Something to investigate as you deepen your own programming expertise.